Hello. We are looking at chapter 2 now, entitled Applications of Differentiation. And we start with 2.1, section entitled, we're going to look at everything, so 2.1 through 2.7, all sections. We're not skipping anything here. Using first derivatives to find maximum and minimum values and sketch graphs. So that's 2.1. I'm assuming you you read about the critical numbers, and they can come from two different sources. So a critical number could be coming from f prime of c being 0. So a critical number is c if f prime of c is 0, or if f prime of c is undefined, but f of c is defined. So the derivative doesn't exist, but the function exists at that point. So this is what it's called a critical number. Only a critical number can change into a max or a min, depending on the signs of the first derivative. So I'd like to look on page 212. And let's say we start with problem 18. In problem 18, we are given a function which is f of x. One more time, page 212. F of x is x to the fourth minus 2x to the third. We're asked to find everything we can about this function and sketch its graph. First of all, we need to determine its domain. That's the very first step in finding anything about the function. I'm going to use a chart that is my preference. You do not have to use this chart if you don't want to. If you have a different way, or if you like the book's method, it's up to you. I accept any method as long as it can be explained, it's legitimate, and it gives a correct results. So first of all, right here, I'm going to present the domain. Well, this is a polynomial function, and it's degree 4. All polynomial functions are defined everywhere. So the domain of this function is everything. And then I'm going to, as the second step after domain, I'm going to try to find whatever I can about the function. The function is in the middle, the first derivative at the top and the second derivative at the bottom. So what can I find about the function? First of all, I can find the limit as x approaches negative infinity from x to the fourth minus 2x cubed. Which of these two terms is more powerful? Of course, this one. Assuming I replace x by negative infinity and I raise that to the fourth power, and that will be positive infinity. So the limit as x approaches negative infinity from the function is infinity. I will determine the same thing for the other side of the function, and nothing changes. This is less powerful than x to the fourth. X to the fourth dictates, so plug in infinity, it's infinity, or positive infinity. What else I can find about the function? From the function itself, I can find the x-intercept. The x-intercept is determined when y is 0, or x to the fourth minus 2x cubed equals 0. I expect 4 solutions. Even if they're all the same, I expect 4 solutions because the degree is 4. I factor out x to the third. I have x minus 2 left, and here are our 4 solutions. 3 times x equals 0. 3 times because the power is 3. And then x equals 2 is the other option. I summarize the information back in the chart. So when x is 0, y is 0, When x is 2, y is 0. There's nothing else I can find about the function from the function itself. X and y intercepts and the limits. One other thing I could talk about right here is symmetry. I know that if I replace x by negative x in this function, negative x to the fourth power does not change. It's still x to the fourth. But negative x to the third power will be negative x to the third times negative 2 will be positive 2x to the third. There are three possibilities. One possibility is that this equals the function itself, which makes the function even, symmetric with respect to the y-axis. Is this the case? No. This is f of negative x, but this is not f of x. This is f of x. So this is not an even function. The other possibility is for f of negative x to equal negative f of x. It's not the case, because negative f of x will be negative x to the fourth and plus 2x to the third. So it's not the case. So this will be an odd function, symmetric with respect to the origin. So it's none of the above. So this function is not symmetric. In my next step, I will study the first derivative, find its critical numbers and its sign, and I'll come back to this chart. So my page 2. Our function was, one more time, I'm copying it here, f of x, x to the fourth minus 2x cubed. So therefore, f prime of x is 4x to the third minus 6x squared. I will factor out 2x squared, and what is left is a 2x and minus 3. Why? Because 2x squared times 2x is 4x cubed, and 2x squared times negative 3 is negative 6x squared. And now I will set this equal to the first derivative equal to 0, and I will say f prime of x is always defined. It's a polynomial function. So no critical numbers can ever come from f prime being undefined. That's not an option for this function. Critical numbers can come only from f prime being 0. When I set this equal to 0, 2x squared 2x minus 3 equal to 0, I expect 3 solutions because the degree is 3. So here they are. I divide both sides by 2. So 2 solutions are x equals 0. The other solution is x equals 3/2. I go back to my chart. Where are you, chart? Here it is. So I have 0 and I have 3/2. Well, 3/2 is 1.5, so it's right in here. So now I'm going to study the sign of this expression and put the sign here. I pick a number to the left-hand side of 0, like negative 1. This is positive always. 2 times negative 1 is negative 2 minus 3 is negative. I'm going to pick a number here, which is, let's say, 1. 2 minus 3 is still negative. And this is always positive, so it's also negative. I'm going to pick a number here, let's say 2. 2 times 2 is 4. 4 minus 3 is 1. This is positive. This is positive. Everything is here positive. Coming back to my chart for a moment, I have to make sure that these two rows work well together. This row with this row. This is the moment of truth right here, right now. From positive infinity to 0, the function is obviously decreasing, and this is supported by the first derivative. So a function that is decreasing has a negative slope. A decreasing function has a negative slope. So yes, the slope is negative and the function is decreasing. From positive infinity, decreases to 0. Now, I have to plug in the function 3/2 before I continue. I need a number here. I grab my calculator in y equals. I put in this function, x to the 4th minus 2x cubed. And I go to second and table, and I plug in 1.5, which is 3/2. Press enter, and I get negative, I'm going to write negative 1.7 approximately. So I continue. So now from 0 to negative 1.7, the function is decreasing, and that is also shown by the sign of the first derivative. From negative 1.7 to 0, the function is increasing, obviously, from a negative number to 0, and this is supported by the sign of the first derivative. If a function is increasing, then the slope is a positive slope at any point. So from negative 1.7 to 0, the function is increasing, and that is supported by the sign of the first derivative. From 0 to infinity is also increasing, supported by the sign of the first derivative. Now I'm going to study the second derivative and see what happens here. So back to my paper. So I have the second derivative now. Here it is. Here was this first derivative. 4 times 3 is 12. X squared minus 12x. I factor out 12x, and I have x minus 1. So now the second derivative could be 0. Degree 2, I'm expecting 2 solutions. When x equals 0 or when x equals 1. Go back. Oops, it's kind of crowded here. I should rewrite my chart, remake my chart, because 1 is now, I have to squeeze 1 in here. Everything has to be in ascending order. So 1, 0. Go back to my calculator, and in y equals, which is very simple, it's 1 minus 2. So that is negative 1. Negative 1 here. 1 comma negative 1. Now I study the sign. I had 0 as well, and 0. Now I have to study the sign of the second derivative, and here it is. I pick a number to the left-hand side of 0, let's say negative 1, negative, and negative, so it's positive. Let's say I pick a number like 0.5. This is positive, but 0.5 minus 1 will be negative, so then the whole thing is negative. Finally, when I pick 2, 2 minus 1 is 1. This is positive. The rest is positive. This is the study, how the information that we have now from the second derivative is this. Whenever the second derivative is positive, the function will be concave up. Whenever the second derivative is negative, the function will be concave down. And same theme here. Now, let's identify these points. We're discussing point 0, 0. The first derivative does not change sign, so that cannot be a max or a min. But the second derivative changes sign at this point. So the point 0, 0 is an inflection point. IP, inflection point. I'm going to write this down in a moment, one more time. Now what happens here with 1, negative 1? 1, negative 1 is also an inflection point because the second derivative changes sign from negative to positive. So 1, negative 1 is also an inflection point. Let's see what 3/2 negative 1.7 represents. This is the critical number, and this is also a critical number. However, the derivative does not change sign. But this is a critical number at which the first derivative changes sign from being negative, 0, and then positive. Negative, 0, and then positive, which makes this a local min. So 3/2, negative 1.7 is a local minimum. I'm going to write them down one more time. So 0, 0, and 1, -1. Inflection points. And 3/2, -1.7, approximately local min. We are ready now to graph this function. Okay, all I need now is my chart. And here's what my chart says. My chart says that the function it's coming from positive infinity, decreasing and opening upward, and it crosses at 0, 0, which is the origin. So it's coming from positive infinity, opening up and crossing at the origin. From positive infinity, decreasing, opening up, and crossing at 0, 0. Now, at 1, -1, 1, -1, this point, the function, so at this point, the function is going to change concavity. So 0, 0, and then it starting opening down, still decreasing. So it's decreasing to this point, which is 1, -1. So this was an inflection point. What is an inflection point? Sorry. What is an inflection point? This is an inflection point. The function changes at that point concavity from opening upward to opening downward. This is not a max or a min. This is an inflection point. Opening upward, inflection point, opening downward. So here is opening upward at this point, the inflection 0, 0. It changes concavity. It all of a sudden it opens downward until 1, -1. At that point, again, it changes. At this point, it changes concavity. It opens upward, and it continues to decrease to 3/2, -1.7. 3/2, -1.7. I should have stopped a little bit further to the left. And then I'm going to say that this is 2. And this is 1.5. So now the function at this point has a local minimum. And it will continue to increase, crossing at 2, 0, going towards infinity. And opening upward. And this is the graph of the function x to the 4th minus 2x to the 3rd. This is basically I extended to 2.2 where it's presented, where your book presents the concavity and the second derivative test. What does the second derivative test say? I'm going to write this down in a minute. Every time where at every point where the first derivative is 0, the function could open upward, like in this situation. At this point, this is not a max or min. So the first derivative is 0, but this is not a max or min. So I cannot apply the second derivative here, second derivative test. What happens at the other point where I know it's a local minimum? Another way of determining that it's a local minimum, assuming I don't study the sign of the first derivative, but I know that at 3/2 the derivative is 0, and I know also that the second derivative is positive. That means that this must be a local minimum, because if the first derivative is 0 and the second derivative opens up, in other words, it's positive, then this must be a local minimum. And that's what the second derivative test shows. I would like to move on to section 2.2, and I'll choose a problem from there. And we're going to go through the same steps one more time. This time I would like to choose a slightly more complicated situation, like, for example, not a polynomial function, because we've seen a polynomial function already, but let's say problem 38 in 2.2, 38 on page 232. 38 on 232. 38 on 232. This is f of x equals x minus 1 raised to 1/3 and plus 3. We're asked to do the same thing. Just determine everything about the function, first derivative, second derivative, and graph the function. Okay, first of all, a reminder, this is nothing else but the cube root of x minus 1 plus 3. I already know how to graph this function using transformations from other courses, but let's assume we don't know that. First, I have to determine the domain of this function. And then I'll study the function. And then at the top, its derivative, and then the second derivative. Okay, so the domain of a cubic function, this doesn't give us anything about the domain, is all real numbers. An odd index requires the quantity under the radical to be greater than or equal to 0, but that's not the case for an odd index. Odd index exists from any number. So negative infinity to infinity. I'm going to determine limit as x approaches negative infinity. So I know what happens here. Of the cube root of x minus 1 and plus 3. When I plug in negative infinity here, this is negative infinity. The cube root of negative infinity is still negative infinity, and plus 3 is still negative infinity. The same thing with limit as x approaches infinity from the cube root of x minus 1 plus 3. Same thing, infinity minus 1 is infinity, the cube root of infinity is infinity, infinity plus 3, infinity. Now I would like to determine what happens when x is 0. That's the y-intercept. So f of 0 will be 0 minus 1 is negative 1, the cube root of negative 1 is negative 1, negative 1 plus 3 is 2. So 0, 2. Now let's find f when f of x is 0 for the x-intercept, which makes the cube root of x minus 1 plus 3 equals 0, or the cube root of x minus 1 equals negative 3. We have to raise both sides to the third power. X minus 1 equals negative 27, of x equals negative 26. Adding 1 to both sides. So add negative 26, function is 0. That's all I can determine about the function from the function itself. Now I will find the first derivative. If you remember, in order to find the first derivative, I will prefer this notation, not this. I bring down the power, 1/3, times x minus 1 to 1/3 minus 1, which is negative 2/3, plus 3 prime, which is 0. So this is nothing else but 1/3, the cube root of x minus 1 squared. In the next step, I have to find the critical numbers. Critical numbers. They can come from two sources. Not necessarily for every function, but they can come from two sources, from f prime of x being 0, or from f prime of x being undefined. However, this function can never be 0. A fraction is 0 only if the numerator is 0, but the numerator doesn't have x in it, so it's only 1. It can never be 0. So none from here. However, this function is undefined at x equals 1. If you plug in 1 here, 1 minus 1, we get 0. And 0 times 3 is 0. 1 divided by 0 is undefined. So this is the only critical number. But the function, the derivative is undefined. So at 1, the first derivative is undefined. So will the second derivative. However, the function exists at 1. So plug it in. 1 minus 1, 0. 0 raised to 1/3, 0. 0 plus 3, 3. Lastly, here, I notice one thing about the first derivative, that since this is always a positive number, the whole thing will always be a positive number. So go study the sign, always positive. The function must be increasing at all times. Now let's see, again, the moment of truth. These two have to go together. Let's see. Excuse me. From negative infinity to 0. Is the function increasing? Yes, and this is supported by the sign of the first derivative. From 0 to 2, yes, it is increasing, and the sign says the same thing. From 2 to 3, it's increasing, yes, and the sign says the same thing. And from 3 to infinity, it's increasing, so the sign says the same thing. And now I know that these two work well together. Now I have to continue with the second derivative. Very good. So here's the first derivative. I like this form when I differentiate. So I get the second derivative, which is 1/3 in front times negative 2/3 times x minus 1 to negative 2/3 minus 1, which is negative 5/3. I forgot to mention that x minus 1, I have to use the chain rule, but x minus 1 prime is 1. So you can say here times 1 if you want. So 1/3 times negative 2/3 times x minus 1 to negative 2/3 minus 1, which is negative 5/3. What we have now, we have negative 2 divided by 9 and the cube root of x minus 1 to the 5th. F double prime is never 0. It's a fraction and the numerator does not have x in it. It could never be 0. So coming back to the chart, I need to study the sign of this. So I will plug in to the left-hand side of 1. Let's say I plug in 0. 0 minus 1 is negative 1. Negative 1 to the 5th is negative 1. The cube root of negative 1 is negative 1 with minus in front. So this whole thing will be positive. So I expect this to happen. And on the other side, let's say 2. 2 minus 1, positive, 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 but there is a negative in front. So I expect the graph to look like this. There are no values at which the first derivative changes sign. So there is no max min. However, 1, 3, because the second derivative changes sign, 1, 3 will be an inflection point, an IP. Let's graph the function. So okay, I look at my chart, that's all I need. Nothing else matters right now. So I see that the function is always increasing. It's coming from negative infinity. It crosses the x-axis at negative 26, 0. So I'm going to say that this is negative 26, 0. And it goes up to 0, 2. And then at 1 is 3. And I know that this is an inflection point. So the function increases from negative infinity to 3 opening up. At this point, changes concavity at 1, 3, 1, 3. Changes concavity, opening downward, going towards infinity. This is the graph of f of x, the cube root of x minus 1 plus 3. So coming from negative infinity, crossing at negative 2, 0, it's a little bit weird because my measurement unit is not good. I couldn't go too far, so I can present negative 26, 0 better. So opening upward, according to the chart, has an inflection point at 1, 3, changes concavity, and continues towards infinity, increasing towards infinity. I would like to look at a word problem here. And on page 232, problem 107. And we are told that a person coughs when a foreign object is in the windpipe. The velocity of the cough depends on the size of the object. Suppose a person has a windpipe with a 20 millimeter radius. If a foreign object has a radius r in millimeters, then the velocity v in millimeters per second needed to remove the object by a cough is given by. Complicated, looks like. Okay, 20 r squared minus r cubed for r between 0 and 20, where k is some positive constant. For what size object is the maximum velocity required to remove the object? So find r that gives the maximum velocity. Very good. In this situation, I have to determine v prime of r because I want to find maximum v. In order to find maximum v, I have to find the derivative of v. So this is k. Inside, I differentiate 40r minus 3r squared. Now I have to find the critical number, or numbers. I set this equal to 0, v prime of r set equal to 0. This is a polynomial function. V prime of r can never be undefined. So no critical number will come from this. Let's see what we have. This is a second degree polynomial. I expect two solutions. K cannot be 0. So 40r minus 3r squared is 0. Factor out r. 40 minus 3r equals 0. So r can be 0, or r can be 40 divided by 3. Not enough. Have to create a little chart this time. And the little chart will have only, so this is my page 5. Very good. So I have r. This time I only need v prime of r and v of r. We have 0. We have 40 divided by 3. And the first derivative is 0 at these 2 points. Now I have to study the sign of the derivative. Here's the derivative right here. Let's say 40 divided by 3 is way bigger than 1. So I'm going to try 1. 40 times 1 is 40. 40 minus 3, positive. I'm going to try 40 divided by 3 is 10 something. So I'm going to try 30. 40 times 30 is 1200. 1200 minus 2700 with 30, right? 1200 minus 3 times 900, 2700 negative. Now this is guaranteed. that this gives a maximum. It's increasing and then decreasing. I have to show why 40/3 gives a maximum velocity. So the radius is 40 divided by 3 millimeters. So 40 divided by 3 millimeters gives a maximum v, which in our case is the velocity in millimeters, of course, per second. The maximum v of our millimeters per second. Now, in section 2.3, we are looking at more complicated functions and graphing more complicated functions, which are rational functions. So 2.3, I'm going to choose a rational function here and graph it. I'm looking on page 247. Let's try problem. Let's say problem 37. Let's start with problem 37 on page 247. So we have the same question here. Graph, determine everything, asymptotes, and so on and so forth. X divided by x plus 2. So we are given a function, this, x divided by x plus 2. Same thing, everything, show everything, function, intercepts, domain, everything possible before we graph it. I have to start with the domain of this function. I have f prime, f of x in the middle, and the second derivative. The only problem we can encounter here is this. The denominator could be 0, so I know that x cannot be -2. Function is undefined, so will its derivatives. Okay, I need this, I need this, I need this, I need this. And the x and y intercepts. So limit as x approaches -infinity from x over x plus 2. When we try to determine limits of rational functions, first of all, one option, one possible route would be this. The degree of the top is 1. The degree of the denominator is 1. So I will factor out x. X times what is x? Well, 1 plus x times what is 2? Well, it must be 2 over x. At this point, I simplify x, and I know that limit of 2 over x as x approaches infinity or -infinity, this must be 0. 2 divided by a huge number is almost 0. So this approaches 0. 1 plus 0 is 1. 1 divided by 1 is 1. When a function value approaches a number as x approaches -infinity or +infinity or both, this becomes y equals 1. Y equals 1 is a horizontal asymptote. Horizontal asymptote 1. It will be the same thing at the other end. So when x approaches infinity, I didn't change anything. I did not. The sign was not involved anywhere. It will come up with the same answer. So y equals 1 is a horizontal asymptote at both ends. This does not always happen. but for rational functions like the ones we are looking at right now, yes. Now I have to determine the limits left and right of -2. Next page, page 6. Limit. As x approaches -2 from the left, from x divided by x plus 2. The numerator is a negative number, the denominator is 0. If you remember, we know that a situation like this, a number over 0, always turns into infinity, negative infinity, or DNE, one of these. Well, -2 from the left, -2.1. -2.1, -2.1 plus 2, negative. Negative of a negative, positive. Limit, as x approaches -2 from the right, of x over x plus 2. It's still the same thing, sorry, a negative number divided by divided by 0. So it's negative here, sorry. -2 from the right-hand side is -1.9. Negative over positive. That makes it negative. Come back to the chart. Infinity on the left, negative infinity on the right. Finally, I have to find f of 0. F of 0 is 0. And if I set the function equal to 0, I will get the same thing, that x equals 0. I cannot find anything else about the function from the function itself. I have to move on to the first derivative now. So the first derivative, remember this is a ratio. It's x divided by x plus 2. The first function prime, the top function prime, is 1 times the denominator, minus the top function times the denominator prime, which is 1, over x plus 2 squared. Don't try to simplify anything, it's not possible. So this is x plus 2 minus x divided by x plus 2 squared. These two go away. So it's positive 2 divided by x plus 2 squared, which is never 0. And it's never undefined where the function is defined. So there are no critical numbers whatsoever. Furthermore, this function is always positive, no matter what number you plug in, because it's x plus 2 squared. So I come back to my chart. I put the sign of the first derivative as being always positive. Now I have to make sure that these two rows go well together. Otherwise, I have a mistake. So from 1 to infinity, the function is increasing, and that is supported by the first derivative. From negative infinity to 0, the function is increasing, and that is supported by the first derivative, the sign of the first derivative. From 0 to 1, yes, positive, because it's increasing. I will study the second derivative now. So this is the first derivative, but I would like to present it like this. It's easier to differentiate. So therefore, the second derivative is, bring down the power, -4, x plus 2 to -3, times the inner function prime, which is 1. So this is -4 over x plus 2 to the third. Again, never 0. A fraction that does not have x in the numerator can never be 0. But I have to study the sign of this expression. So to the left-hand side of -2, I'm going to plug in -4. -4 plus 2, -2. -2 cubed, -8 with negative in front. So this will be positive, which makes the function open upward. On the other side, I'm going to plug in 0. 0 plus 2 is 2. 2 cubed is 8. 4 over 8 with minus in front. That's negative. So then the function will open downward. The function is not symmetric, so I'm ready to graph it using my chart. Nothing else. I don't need anything else. So here's I want to mention one thing here that I forgot. Every time a function approaches infinity or negative infinity, as x approaches -2 from either side, that is the typical situation for x equals b equals -2, vertical asymptote. So when I graph a function with asymptotes, I have to start by graphing the asymptotes. And here they are, two asymptotes here. Y equals 1 and x equals -2. Now we're ready to read the chart and graph the function. Here it is. The function from approaching 1 increases to infinity on the left-hand side of this asymptote. From 1 increasing to infinity on the left-hand side of the first asymptote, opening upward. On the other side, it crosses at 0, 0. It opens downward at all times. It increases at all times, coming from negative infinity, crossing the x-axis at the origin and going to 1, approaching 1. And this is the graph of x over x plus 2. I would like to look at a word problem here as well. Let's say problem 65 on page 248. My page 7. 65. One more time, 248. Cost of pollution control. Cities and companies find that the cost of pollution control increases along with the percentage of pollutants to be removed in a situation. Suppose that the cost C in dollars of removing P% of the pollutants from a chemical spill is given by C of P equals 48,000 divided by 100 minus P. P is in percent and C is in dollars. Find C of 0, C of 20, C of 80, and C of 90. Okay, so there are 0, 20, 80, and 90. I will grab my calculator, put in y equals this function, 48,000 divided by 100 minus x. And I am going to put in 0, oops, that's not what I meant, second and table first. 0, 20, 40,000, 100 my, oh, okay. So 0, 20, one more time, 0, 20, 80, and 90. Okay, so I have 480. And of course, it's dollars. 600. For 80 is 4,800. And for 90, oops. And that is 2,400. Part B. Find the domain of C. Of course, 100 minus P cannot be 0. So P cannot be 100. So domain, between 0 and 100. Percentage cannot be negative, and it cannot be more than 100 anyway. Sketch a graph of C. Can the company, part D, can the company or city afford to remove 100% of the pollutants due to the spill? Explain. Perfect. So now we are trying to graph this function. So that's part C, graph C of P. First of all, I will graph C of P after I do some analysis in a moment, but obviously the graph cannot show anything else to the bottom, below the x-axis or the p-axis, or to the left of the cost. Cost cannot be negative, and percent cannot be negative. Very good. I already know that this function, first I have to determine its limit, as p goes to 100 from the left of 100, 48,000 divided by 100 minus p. And we also know that C of 0 is 100 minus 0 is 100, and simplified we already have it, 480. So 1, 2, 3, 4, 5. That will be our first point, 0, 480. Now, when P approaches, of course, we'll get that in a minute. This is a vertical asymptote, x equals 100. As P approaches 100 from the left, like with 99, let's say, the numerator is positive, the denominator is 0 with 100, but it will be positive as well. So the limit will be infinity. Therefore, it's guaranteed that x equals 100 is a vertical asymptote. Let's also look at C prime. When I determine C prime, I'll come back and replace this function by 48,000 multiplied by 100 minus p raised to -1. It's easier to differentiate. So I bring down -1, so it's -48,100 minus p raised to -2 multiplied by the inner function prime, which is -1. So then we have 48,000 divided by 100 minus p, everything squared. We are ready for our chart. So this is my page 8. So P, the domain is between 0 and 100. And C prime of P, C of P, and we'll see in a moment if we need a second derivative. So at 0, we already know it's 480. And at 100, because the function is undefined at 100, the limit on the left of the vertical asymptote is infinity. Now, the first derivative is always positive. Always positive, and it's never 0. Never 0. Always positive. So now these two rows have to work together from 480 to infinity. Yes, the function is increasing, and so is this. Now, let's continue and find the second derivative. Let's see what the second derivative tells us. So I have 48,000 times this prime. So 48,000 times -2 times 100 minus p to -3 times the inner function prime, which is -1. So therefore we have 96,000 divided by 100 minus p to the third power. All we care about is the sign. So when this is 0, when p is 0, this will be positive. When p is 1, this will be positive. So, and so on and so forth. So the function will be always opening up. So, as expected, this is its minimum value, and it's going up to infinity. So here's the graph. So and for the final question, can the company or city afford to remove 100% of the pollutants? Well, 100% is never attainable. It will mean a cost that is infinite. So no, the answer is no. The company can never remove 100% of the pollutants. Now, in section 2.4, we are mainly talking about the same thing. However, the interval that will be given to us is a closed interval. I'll explain in a minute. On page 258, I'm looking at really any problem here. Let's try 28. So problem 28 on page 258. And here's the function. X cubed minus x to the fourth, f of x cubed minus x to the fourth. And the closed interval is given to us as -1, 1. So let's read the question. The question is asking us to find the absolute max and minimum values of each function. So again, in this situation, we're not asked to graph, but we're asked to find max, min. A local max I will add, and local min, and absolute max and absolute min. So in this case, the domain is given. We don't have to find anything about that. So now f prime and f of x. No second derivative is needed here. So I go right ahead to find the first derivative. So this is 3x squared minus 4x to the third. I factor out x squared and 3 minus 4x. Degree is 3. I have to find 3 solutions from f prime being 0. There is no critical number coming from f prime undefined. So I expect 3 solutions. However, 2 of them are the same, x equals 0, and the other one is x equals 3/4. So I go back to my chart, 0 and 3/4. I study the sign of the first derivative. But there is not much to study because this is a positive number. And this expression is a linear function with a negative slope. So if I plug in a number to the left of, let's say, or at 0, that will be 0. I can. So -0.5 or positive 0.5. It doesn't matter. One or the other. Let's say -0.5. This will be positive. And I plug in 1. This will be negative. At this point, I take my calculator and I put in the function in the graphing calculator, which is x cubed minus x to the fourth. And I determine these values for the function -1, 0, 3/4, and 1. So -1, 0, 3 divided by 4, and 1. Now I'm copying those numbers. At -1, the function is -2. At 0, the function is 0. At 0.75, the function is positive 0.1. And at 1, the function is 0. Okay, so now I'm going to create a little graph. Really no graph, but I'm just putting the values so I can see them. So here are the values that I have. I have -2. I have 0. I have 0.1. And I have 0. This is no graph. I'm just presenting the points so I know which one is the maximum, which one is the minimum. This is at the end point of the interval. It cannot be local min. No end point can be a local min. So this is only the absolute min, the smallest possible value that the function has. Now this is in the middle of the interval or somewhere in the interval, so it is a local max, but also an absolute max. This one is nothing. What about this one? Nothing. It's not the absolute max. It's not the absolute min. It cannot be not local because it's at the end point of the interval. And it's not absolute. It's not absolute minimum. It's not absolute maximum. Not absolute. If you want, we can put them back on the chart. So this is the absolute minimum. And this is the absolute max. This and this don't mean anything. 0, 0, nothing. 1, 0, nothing. This is how we study a function on a closed interval. All problems are similar. I like to look at a word problem here. Let's yeah, why not? Problem 103. 103 on page 260. And let's read the problem first. We are given a total cost and a total revenue functions for producing X items. So we are given C of X as the cost function. And it equals 5,000 plus 600X. We are also given the revenue function, which is -1/2 X squared plus 1,000X. We're asked now, we're given that X is between 0 and 600. And we're asked to determine the total profit function. No problem. Profit is revenue minus cost, which is -1/2 X squared plus 1,000X minus 5,000 minus 600X. So it's -1/2 X squared plus 400X minus 5,000. And that was part A. In part B, we're asked to find the number of items X for which the total profit is a maximum. So we want to maximize the profit. In order to find the maximum, I will find the first derivative, which is -X plus 400. I will set it equal to 0. And from here I get that X equals 400 units. However, this is not enough. I have to prove, I have to show that this number, 400, gives a maximum. Okay, so in the first derivative, I plug in 0. When I plug in 0, I get positive. When I plug in 1,000, -1,000 plus 400 is negative. So this is positive and negative. This is guaranteed that 400 gives a profit. It is a maximum profit. The rest of the final sections, 2, 5, 2, 6, 2, 7, will be in the next video. Thank you.